July 1st, 2025, NASA's Atlas survey, the world's cosmic warning system, detects a new interstellar visitor tearing into the solar system at impossible speed. At first, it looks like another comet, but experts realize something doesn't fit. Its brightness suggests a solid mass up to 20 kilometers wide, yet objects this massive from outside our solar system are supposed to be vanishingly rare, barely glimpsed once every decade. For days, astronomers struggle to explain a trajectory tuned so precisely it brushes past our planets, a statistical fluke bordering on impossible. And then, the system registers a strange pulse that warnings say is coming fast, straight for Earth. What secret is Comet 3I/Atlas sending our way? And why are scientists suddenly silent? At 3:17 a.m. UTC, Atlas's automated alert system flagged an anomaly on its nightly scan, a sharp, rising streak, brighter than anything cataloged that month. Duty astronomers at the Rio Hurtado site jolted into action, cross-checking the feed against known asteroids and comets. Nothing matched. The object's coordinates were relayed to the Minor Planet Center, triggering a rapid chain of confirmations from telescopes in Hawaii and California. Within the hour, the internal alert level rose. The software's initial size estimate, up to 20 kilometers wide if the object was solid, set off a wave of disbelief. That's the kind of mass that, if it hit, could erase continents. But here, the numbers didn't add up. The object was moving too fast for anything from the Oort cloud or Kuiper belt. Its path cut across the solar system on a hyperbolic arc, a signature of something born far beyond Neptune, maybe even outside the sun's grasp altogether. On the internal comms, one astronomer typed, "Check the residuals, this can't be real." But every recalculation pointed to the same conclusion. The object wasn't bound to the sun. The team watched as the brightness curve spiked, then held steady. No sign of the flickering or fading that would betray a loose cluster of fragments. Instead, the signal's consistency suggested a single, coherent body, reflecting sunlight with unnatural regularity. As the minutes ticked by, the network's automated warning system escalated. A mobile alert pinged planetary defense contacts, and a red banner flashed across the Atlas dashboard. Possible interstellar object. Confirm trajectory. Assess risk. The urgency wasn't just about the object's size or speed. It was the calculated precision of its approach. The numbers pressed in. Closest approach to Earth, 1.8 astronomical units. Velocity, off the charts. Time to perihelion, just weeks away. In the control room, silence stretched as the team realized what they were watching. This wasn't a routine comet. The system had just caught something the textbooks barely imagined. A visitor from another star, barreling toward the heart of the solar system and sending a pulse that no one could yet explain. Interstellar visitors are so rare that before 2017, not a single confirmed object from outside our solar system had ever been seen. When Oumuamua passed through, it was a once-in-a-century event. Borisov followed 2 years later, a streak of icy debris that barely left a mark. Now, with 3I/Atlas, astronomers are confronting a pattern that defies easy statistics. The best surveys, scanning the sky every clear night, expect to catch one genuine interstellar body about once every 10 years. That's a rate so low you could work an entire career and never witness one firsthand. The shock isn't just in the detection, but in the numbers that followed. Even the most optimistic models suggest that for every interstellar object caught, thousands, maybe millions, slip by unseen, too dark, or too distant to trigger an alert. That makes Atlas's catch a kind of cosmic lottery win. Dr. Petra Sandu at the European Space Agency put it bluntly. 3I/Atlas is the brightest and most symmetrical interstellar visitor we have ever seen, almost as if it wants to be noticed. Size only deepens the riddle. Early calculations, based on the object's brightness, hinted at a body up to 20 kilometers across, larger than Manhattan and 1,000 times more massive than Borisov. Later refinements with the Hubble and James Webb telescopes trimmed that estimate, settling on a nucleus somewhere between 1/3 of a kilometer and just over 5 kilometers wide. Even at the low end, it's a giant among known interstellar travelers, and the odds of such a large, active comet crossing our path are vanishingly small. The scarcity of material in interstellar space makes these numbers hard to swallow. There simply isn't enough debris drifting between stars to expect something this big, this bright, to show up in our backyard. Each new data point forced astronomers to ask, how many more are out there, hiding in the dark? And if this is what we can see, what have we already missed? The sense of improbability lingers, feeding a quiet dread that the universe might be less empty and less predictable than anyone thought. On paper, an interstellar object careening into the solar system should take any path at all, north, south, steeply tilted, or nearly perpendicular to the planetary plane. Yet 3I/Atlas threads a route within just 5 degrees of the ecliptic, the same narrow disk where every major planet orbits. Celestial mechanics analysts ran the numbers, hunting for precedent, but the odds of this kind of alignment are so remote that even conservative models struggle to account for it. For a random visitor from the galactic dark to arrive so neatly in step with the solar system's geometry, the chance is less than 1 in several hundred, maybe even lower, depending on the assumptions about survey bias and sky coverage. Add to that the sequence of planetary encounters. Atlas's predicted path brings it near Mars, then Venus, then Jupiter, 3 major worlds in succession, all within a single solar pass. Planetary scientists compared this to a cosmic trick shot. The odds of a random interstellar object threading that series of close flybys without being captured or ejected push the bounds of plausibility even further. Some models suggest a probability below 1 in 10,000 for such a sequence, though with only 3 known interstellar objects. The true statistics are anybody's guess. Each step of the trajectory, each planetary near miss, stacks improbability atop improbability. The result is a path that looks less like a natural accident and more like choreography, an arrival so precisely tuned, it forces astronomers to question whether they're seeing the universe's randomness or something else entirely. If you followed these rare interstellar guests before, you'd know the first one confirmed was Oumuamua in 2017. That elongated object slipped through the solar system without a tail, spinning end over end, and reflecting light in a way that never quite fit any natural template. Its brightness rose and fell in odd patterns, and its path changed slightly, as if nudged by invisible hands. Yet, telescopes caught no trace of outgassing. For months, the debate over its true nature, asteroid, comet, fragment, or even artifact, echoed across astronomy journals and late-night talk shows alike. 2 years later came Borisov. Unlike its predecessor, Borisov looked every inch a classic comet. A fuzzy ball, a tail streaming out behind, and an unmistakable cloud of dust and gas. Its chemistry matched what you'd expect from a body forged in the cold outskirts of some distant star. Borisov's visit was brief and less mysterious, but it proved that interstellar comets could resemble the ones born closer to home. Atlas, though, doesn't fit either mold. Add to that its unusual glimmer and consistent brightness, and suddenly you have a hybrid, unlike either of its predecessors. There's no classic tail, yet it's far brighter than Oumuamua ever managed. Its surface returns sunlight with a smooth, almost mirrored regularity, and the light curve lacks the chaotic flicker seen in natural tumbling objects. Picture something the size of a city block, shining like a perfectly polished window, moving with a confidence that feels almost deliberate. Scientists who tracked both earlier visitors now find themselves looking at Atlas and asking whether it's a comet, an artifact, or something entirely new. The only certainty is that the old categories no longer hold. Hubble's first high-resolution images offered a puzzle no one could ignore. Instead of the blurry, diffuse glow that usually surrounds an active comet, 3I/Atlas displayed a sharp, forward-facing sheen, a bright spot gleaming ahead of the nucleus, almost like a headlight cutting through the void. Photometric analysis showed something even stranger. The reflected sunlight wasn't scattered in the chaotic way typical of dusty ices. Instead, the surface glimmered with a metallic crispness, its albedo more like polished chrome than frozen rock. Astronomers expected irregularities, a rough patchwork of ice and dust, maybe a few jets of vapor, all tumbling unevenly as the comet spun. But the light curve told a different story. Every rotation, the brightness rose and fell in perfect repeating intervals, as if the object were spinning on a perfectly balanced axis. That kind of symmetry is rare, even among engineered satellites, let alone natural bodies flung across interstellar space. Hubble's imaging teams traced the source of the glint. The leading edge, rather than trailing a tail, reflected sunlight so efficiently it outshone the rest of the coma. At certain angles, the nucleus appeared edged in a mirrored band, a feature that persisted across multiple wavelengths and exposures. No known comet, interstellar or otherwise, had ever exhibited such a forward glow, nor such a smooth, undisturbed surface signature. Add to that the lack of typical flicker or fragmentation, and the evidence begins to suggest something more than chance. Each new scan deepened the mystery, forcing even the most skeptical observers to ask whether they were looking at a natural wanderer or the polished exterior of something built to last the journey between stars. Spectroscopists at the Webb telescope began mapping the surface chemistry of Defying/Atlas, expecting a patchwork of common cometary ices. Instead, their data revealed something harder to reconcile: broad zones where carbon signatures ran uninterrupted for kilometers, as if the surface had been painted in a single, uniform sweep. These carbon-rich regions didn't blend into the expected mosaic of water ice or silicate dust. The readings showed a boundary, sharp, not gradual, where the composition shifted, a pattern more reminiscent of engineered layering than random accretion. Modelers working with the momentum calculations ran into their own wall. For the amount of sunlight 3I/Atlas reflected, and the mass it should have, the numbers pointed to a density far lower than any solid rock or ice. The object responded to solar pressure almost as if it were hollow. Its acceleration under the sun's push didn't line up with a dense, natural core. One calculation, checked and rechecked, suggested a shell just a few meters thick could explain the observations, provided the interior was mostly empty space. That kind of structure isn't found in asteroids or comets, not even among the most porous rubble piles drifting through the inner solar system. Another oddity complicated the picture. Typical comets, especially active ones, vent jets of gas and dust as they approach the sun, creating visible plumes and subtle changes in motion. But 3I/Atlas, even under the scrutiny of high-resolution imaging, showed no sign of these jets. The coma was smooth, its brightness unbroken by the telltale streaks of outgassing. The absence of jets, combined with the low density and uniform carbon patches, left observers with a model that fit neither known comet nor asteroid. The closer the data was examined, the less it looked like anything nature assembles by chance. 48 hours after the first trajectory models hit internal servers, something changed. The public data feeds for 3I/Atlas, live plots, orbital calculators. Even the nightly photometry, suddenly redirected to maintenance pages. No explanation, only a timestamp and a promise of updates. Requests for raw telescope data, usually routine, began returning blank files or heavily redacted PDFs. Entire columns missing, lines blacked out except for generic headers. The usual transparency, taken for granted with Oumuamua and Borisov, vanished almost overnight. Freedom of Information Act petitions poured in from amateur astronomers and academic watchdogs. The responses arrived within days, far faster than normal. But each packet was stripped to the bone, page after page of black rectangles, with only the most anodyne technical jargon left untouched. The blackout wasn't limited to the data. Names of staff once associated with Atlas or Pan stars quietly disappeared from official project rosters. Some profiles on institutional websites went offline. Others resurfaced with new assignments, their comet work scrubbed from biographies. Inside JPL, sources described a tightening of access. Slacks and internal mailing lists that once buzzed with open debate now fell silent. Even routine status updates were rerouted through administrators. The sudden clampdown didn't go unnoticed. Outside observers, used to the open culture of planetary science, began to wonder what could justify such sweeping secrecy, especially when, by every official statement, the object posed no threat. The silence itself became a signal, hinting at discoveries or risks too sensitive for public release. At the far edge of the analysis queue, a new anomaly surfaced, this time not from visible light, but from the deep infrared. As the James Webb Telescope tracked 3I/Atlas, its spectrometers recorded a thermal rhythm pulsing from the nucleus, repeating in intervals so precise they resembled the calibration signals engineers used to test their own instruments. The pulses weren't random. Each burst arrived at a fixed cadence, every 13.7 seconds, with a sharp rise and slow decay, too regular to be explained by rotating ice patches or jets of gas. SETI algorithm teams, usually focused on distant stars, pivoted to run time series analyses on the data. They found the pattern matched no known natural process, not cometary outgassing, not tumbling debris, not solar heating. Adding to the puzzle, Webb's heat maps revealed a subtle but measurable thrust, nudging 3I/Atlas along its path without any visible jets or venting. The object seemed to accelerate in sync with the infrared pulses, as if responding to an internal engine or some hidden mechanism. Signal analysts, confronted with the unmistakable regularity, began to ask whether the pulses were a beacon, a deliberate attempt to be noticed or even to communicate. The silence from official channels, paired with the growing evidence of engineered intent, left a single question echoing through the data rooms. If this is a signal, who or what is sending it? The blackout only deepened the divide. In the vacuum left by official silence, online forums and late-night streams turned into battlegrounds of speculation. Some participants, armed with telescope time and open-source software, tried to reconstruct the missing data. Their efforts produced a patchwork of brightness curves and color maps, none conclusive, but each fueling new theories. One camp insisted on a natural explanation, rare chemistry, a fluke of cosmic billiards, maybe a comet forged in a star system unlike any seen before. Others pointed to the signal's precision, the sharp compositional boundaries, and the near-perfect symmetry as evidence of design. If 3I/Atlas was a probe, they argued, it would look exactly like this, bright enough to draw attention, subtle enough to slip through official channels before the story could be controlled. The debate spilled across platforms. Reddit threads filled with diagrams comparing the pulse intervals to Earth zone calibration beacons. Discord servers hosted impromptu roundtables, with engineers and hobbyists dissecting every fragment of leaked photometry. Some claimed to see encoded patterns in the infrared rhythm, a message perhaps, or a test to see if anyone was watching. Others warned against wishful thinking, reminding everyone that the universe is stranger than fiction, but not necessarily deliberate. What lingers is not a consensus, but a tension. No one can say for certain what 3I/Atlas is, or why it arrived on such a path, shining so insistently, and then slipping behind a wall of secrecy. The object itself is already receding into the dark, but the questions it leaves behind refuse to fade. In the end, the story may not be about answers, but about the unsettling realization that some signals are meant to be noticed, and that sometimes the most haunting message is the one that remains unresolved. On July 1st, 2025, NASA's Atlas survey detected 3I/Atlas, only the third confirmed interstellar object in recorded history. Its estimated 20-kilometer diameter and hyperbolic trajectory set it apart from all previous finds. Over the course of weeks, astronomers documented its unusual orbit, improbable planetary flybys, and distinct surface features, including a forward glow and highly reflective exterior, using data from Atlas, Hubble, and James Webb. Yet, as observations intensified, official data portals went offline, and key documents were heavily redacted. Scientists noted rhythmic infrared pulses and unexplained motion, raising further questions. To this day, the true nature and origin of Defying/Atlas remain unknown, with critical data still unreleased. What is clear is that each new interstellar visitor challenges our understanding of the cosmos, and that the mysteries of 3i/Atlas will shape scientific debate for years to come.